In the Bristol work package on subshot noise imaging, we're investigating the ways that we can develop better light sources in order to improve the quality of imaging and sensing. So we know that imaging and sensing are very important in many fields of science and technology. And one of the main limitations is the light source itself, because all light sources exhibit some form of noise. So this can be intensity noise, classical noise, which leads to degradation of images, like you can see here with this sort of smearing effect. But even if we're in principle able to reduce this completely by better engineering, we always have this fundamental limit, which is that light is composed of photons. So for classical sources, that means at low intensity, you always have this limit of shot noise, which is this kind of grainy effect that you see in these very dark images here. The way we get around this in our work at Bristol is we work with pair photon sources. So what this means is we generate light as correlated pairs of photons. We're then able to split these pairs. And if we count one photon from the pair, that then gives us a perfect intensity reference for exactly the number of photons that we send through our sample that we're imaging. And you can see here the kind of improvement in the quality of images this allows us to generate, looking here at equivalent light level measurement for a photon source and a classical laser source. And now we're trying to take this approach and push it to higher intensity levels. So this is a recently developed demonstrator. You can see these red and blue beams here, which are now bright enough to be visible, but they still follow this generation on a pairwise basis. That means that the intensity levels of these two beams are perfectly correlated. So as I said, we've actually been able to prove subshot noise performance in both of these kind of systems. But it's really this high intensity one that we're focused on mostly now. So we generate light in an optical fiber. This is a special kind of microstructured fiber. And by controlling the structure of the fiber itself, we can select the wavelengths we want to generate. So here we were targeting novel wavelengths near 450 and 600 nanometers, which are useful wavelengths. And in principle, we can select other wavelengths quite easily. And the other nice thing about this is we're able to push into this regime of exponential gain of the process, where we very quickly move from the single photon level of brightness up to these really bright quantum states where we can start competing with classical laser measurements. In terms of the end users and applications, so the technology from the photon source that I described has already gone into a commercial product released recently by Thor Labs. And we hope this will allow researchers in fields such as quantum communications or metrology to be able to start doing their experiments without first needing to become experts in how to design light sources themselves. And we're really excited about these bright intensity correlated sources because we think there's not really any comparable competing products for bright metrology like this at the moment. And this combination of unique wavelengths, high brightness and ultra low noise is really appealing in areas such as life sciences, where you can't just increase your measurement quality by using more and more light. For example, when you're measuring living cells and there's issues like damage thresholds of these systems.